Now I'm recording. Okay, so this is now the end of the 6th week. This is lecture number 11. And we are on chapter 15. So we had started 15 last time. We had done most of 15 last time, in fact. And let's just recap what we did. We first talked about the difference between a parameter and a statistic. A parameter is a number that describes the entire population, usually the thing that you're after. The average height, the average weight, the average lifespan, the average anything. I mean, something about the entire population. We very rarely know this. In fact, if we know it, then why do any data to calculate it or to guess it?
Is this review?
We're starting with review, and then we're going to segue into new stuff. So yes, this is, we did all this last time. I think we did it last time, right?
Yeah, that's why I was double checking.
Yeah. So parameters and statistics. A parameter is a number for the entire population. A statistic is a number that comes from the data, from the sample. And usually what you're going to do is you're going to take your sample value and use it to come up with some kind of guesstimate for the population. For example, here again, the mean income of a sample of 124,586 households was $75,738. This is the sample mean. It comes from the sample. It is a statistic. And we use this statistic to make a guesstimate for the actual mean for all of the households, which is a parameter. And because this sample was extremely large, assuming that the sample was a representative sample, I am fairly confident the average salary for the entire American population is somewhere very close to this value. That's a very large sample. Once the sample size gets very large, by the law of large numbers, our average value hones in on the actual value. This is a very large sample. We talked about the law of large numbers, of course, as a follow-up. The law of large numbers basically just says that as the sample size gets larger and larger and larger, the sample mean gets much closer, or gets very close to the actual population mean that you're after. You never know this, but if the sample size gets large enough, then we are very confident that whatever we get is close. We talked about the difference between the population distribution and the sampling distribution. If I take one piece of data at a time, it's going to have some graph, some density curve, some distribution. But if I take a sample of a bunch at a time, let's say 10 at a time, for example, then my distribution for 10 at a time is going to look different as a general rule than my distribution for 1 at a time. And we have the population distribution, which was the original 1 at a time. And then we have the sampling distribution, which is for a certain amount at a time. So 5 at a time will have a distribution, and 10 at a time will have its distribution, and 100 at a time will have its distribution. And we saw last time we brought an applet in from outside, a very cool applet which shows different distributions. And what we saw was as the sample size increases, the shape of the distribution changed, but eventually they all became what? If the sample size got large enough, those distributions all became normal. Now, if it started normal, then it's always normal. Okay, so if we start with a distribution that is normal already, then any sample size will also be normal. But there's one difference though. If the original population distribution has mean mu and deviation sigma, the sample distribution has the same mean. Its center is going to be in the same location, but the standard deviation gets smaller. It gets thinner in a very predictable way. So if we have a normal distribution whose mean is mu and whose distribution is sigma, and we take a sample at size n, and we use the sample mean instead, it will have the same center, the same mean, the same mu, but it'll be much thinner because its distribution will get smaller. And we're going to do examples of that for sure. And we did examples of that last time as well. And we'll do lots of examples because this is going to be the central theme for the next few chapters. We also talked about the central limit theorem. The central limit theorem we saw very powerfully with the applets that no matter what the original distribution looks like, if the sample size gets large enough, then the sample distribution is approximately normal with the same mean, and again, sigma over the square root of n. How much is the sample size is large enough? When n is large, what does that mean? The basic rule of thumb is that if n is 30 or more, you are good to go. So if n is 30 or more, you can use the normal approximation. Here we have an example, household income, thousands of dollars, and the percent of households. We see most people do not make a lot, so the household income is not very high, and then it tapers off, and you have some people who make lots and lots and lots, but percentage-wise, not many, so it's a right skew distribution. But if you take samples of size 100 at a time, then even though the original distribution is very right skewed, the sample distribution becomes normal looking. That's the central limit theorem in action. Again, here's another example. We have an exponential distribution. This is 1 at a time. This is 2 at a time. This is 10 at a time. And this is 25 at a time. How do I know? I'm just reading the bottom, right? 1 at a time, 2 at a time, 10 at a time, and 25 at a time. So you see that by the time we reach 25, even though we have this very unnormal looking distribution, the sample distribution becomes very normal looking. So we did all that last time. Including an example. We're going to do some examples from the exercises. So let's just see what section 6 is. So let's see what we're doing here. So they're talking about statistical significance. They label it as a star in terms of you can skip this section without detracting from understanding what's going on. The key of this, well, not the key, but we're going to skip it only because we're going to cover statistical significance later. So let's do some exercises. Let's do some examples from here to test our understanding. So let's take a look and find some good ones. Are these only for this section? Or is it starting at 24? Here, check your skills. Let's try that. All right. Lesson number 19. Okay. It says scores on the critical reading part of the SAT exam in a recent year were roughly normal, with mean 495 and standard deviation 118, right? So we have an N of 495, 118 population distribution. This is for 1 at a time. Let's just remind ourselves what everything means here. What does the N tell you in this case?
Sample?
No, capital N, I'm sorry. This the capital N here is telling you what in this notation? That we're dealing with a normal distribution. What does the 495 tell you?
The mean.
The mean. And what does the 118 tell you?
Standard deviation.
Standard deviation, right? So if I was going to label everything in a picture, I would make a normal curve. I would have the mean 495, and I would have the distance between the mean and the inflection point be 118, so that one deviation out is like 613. Now, you choose a simple random sample of 100 students, and you take the average of their scores. Now, let's look at the original distribution for a second. If you took one person at a time, it's kind of unlikely that person would end up over here, right? This is not very high, but it certainly is possible, right? It's not like a 0% chance. Maybe it's like a 10% chance. It's not high, but it's there. But if you took 100 people at a time and average them, how likely is it that you get a result over here? How likely is it that the average of 100 people would be all the way over here?
Low.
Very,
Low.
very low.
Much
Very,
like-
very low, right? Very, very low. So we want to quantify this, and we want to see exactly how to calculate it. So the sample distribution when n equals 100, so we're going to have this is the n equal 100 sample distribution, is also going to be normal, because if the original one is normal, then all sample distributions are normal. And even if the original one wasn't normal, why would I be allowed to approximate this with a normal distribution? I mean, the original one is normal, but even if it wasn't, would I be allowed to approximate this with a normal distribution? And if so, why? And if no, why not?
Can you repeat the question?
We know that the original distribution here is normal. How do I know? They told me. So if the original distribution is normal, then the sample distribution is normal. What I'm asking is, if they did not tell me that the original distribution was normal, would I be allowed to assume that the sample distribution is normal?
No.
Why not? Not saying you're wrong. I'm just asking why not.
Only because it could be either or, and so you can't really specify.
Either or what? What do you mean by that?
It could be normal or not normal.
Okay, that's the question. Is there anything in the problem that allows me to say that it's normal, no matter what the original distribution was like? And the answer is yes. What is it that allows me to say that this is normal, no matter what?
The sample size?
The sample
Because-
size.
Yeah.
Okay, if n is bigger than 30, then you can then unless it's a very rare situation, you can approximate the sample distribution with a normal distribution. Here, what is the sample size?
100.
100, which is way more than 30. Enough that even if I did not know that the original one was normal, I can certainly assume that the sample distribution is normal. So it's normal. What's the mean?
495.
495. If each one individually has an average of 495, then any sample is going to have an average of 495. And what is the new standard deviation?
11.8.
11.8, because you take the old standard deviation, which is 118, and divide by the square root of 100, square root of n, so divide by 10, you get 11.8. So we actually answered both 19 and 20. What will be the answer to number 19, A, B, or C?
C.
Not for the mean.
Oh, for the mean. Sorry, I meant that was for standard.
I
Never
believe
mind.
you.
But
So
that's
what's the
the
answer for 19?
A.
A, and what's the answer for 20?
C.
C. So we just checked the answer. They were very nice. They said, click to display the answer. Well, that's the answer. Let's do another one. Number 21. A newborn baby has extremely low birth weight, ELBW, if it weighs less than 1,000 grams.
I'm sorry, quick question.
Yes.
Just to clarify.
Mm-hmm.
So 11.8 is the new standard deviation for the sample size?
Not for the sample size. It's the new standard deviation for the sampling distribution for that sample size.
Okay.
I mean,
Thank
you could have taken samples of size 82, correct? Or 114 or 74, right? You could take samples of any size you want. Each one of them is going to have a different distribution. So specifically for the samples of size 100, its sample distribution will have a sigma of 11.8.
Okay, thank you.
Okay. So number 21. A study of the health of such children in later years examined a random sample of 219 children. 219, what does that tell me?
Sample size, and it's going to be normal.
It's very large sample size, and therefore I can assume it's normal. So Someone sent me, let's see, what did that person say in chats? It's normal, yes. Or at least approximately normal. So their mean weight at birth was X bar equals 810 grams. This sample mean is an unbiased estimator. So we didn't talk about this term unbiasedness. I didn't skim it, I just skipped it because I really didn't think it was important yet in the course, but just in case there's a homework question on it, let me explain what it means. When you use one thing to estimate another, so when I use the sample mean to estimate the population mean, I have what's called an estimator. Okay, the estimator is the sample mean. It is estimating the population mean. What does it mean to be unbiased? It means that I expect the sample mean to be to give me a good approximation for the actual mean. That's what makes it unbiased. Let me give you a situation of a biased estimator so you can see the difference. If I am going to measure the average height of every American, suppose I take a sample of 100 people. If I use the average of that sample, would that be an unbiased estimator for the actual average? Do I assume that the value that I get from my sample would be pretty close to the true average that's out there?
No.
Sure. I mean, it might not be perfect, but assuming that the sample is good, there's no reason why it shouldn't, right? So on the average, some will be taller, some will be shorter, but my sample average should be right around the actual average. Why not? It's not biased in one way or the other. But if I take the same 100 people and say, you know what? I'm going to take the tallest and use the tallest person as my guess for the average height of every American, would that be a biased or an unbiased estimator?
Biased.
That's very biased because chances are that the tallest person in my sample is not representative of everyone in America, right? It's biased towards that side. I'm still estimating the average height. It's just not a very good estimator because it's biased. So an unbiased estimator is one that I expect to give a value close to the true value. So the sample mean is an unbiased estimator. This means that A, in many samples from the population, the mean of the many values of X bar will be equal to mu. B, as we take larger and larger samples from this population, X bar will get closer and closer to mu. And C, in many samples from this population, the many values of X bar will have a distribution that is close to normal. Well, B has a different name. What do we call B? We gave a name for B. As we take larger and larger samples, X bar will get closer and closer to mu. We call that something. What was that name? Anyone recall the name we gave to the property for B?
Unbiased.
No, forget about biased or unbiased. What do we call B? We called it last week or Tuesday. We gave this a name. As we take larger and larger samples, X bar will get closer and closer to mu. We gave it a name. We called it a law.
The law of large numbers.
That is the law of large numbers. That's got nothing to do with unbiased or biased. That's the law of large numbers. The larger the sample, the closer X bar will be to the mean, to the true mean. C, we gave this a name. Okay, in many samples from the population, the many values of X bar will have a distribution that is close to normal. If the sample size is large enough, X bar will be close to normal. What do we call this one here? We gave this one a name. I'll give you a hint. It's on the page. I'm looking at it.
Is it a normal distribution?
No, this was called the central limit theorem. The central limit theorem said, let's go back to 15.5 for a second. The central limit theorem said that when n is large, the sampling distribution of the sample mean X bar is approximately normal. The larger the population, sorry, the larger the sample, the closer X bar will be to be normal. Let's go back to that question and see what it says there again. The question said, in many samples from the population, the many values of X bar will have a distribution that is close to normal. So all the different X bar values, when I make my distribution, it will be close to normal. That is the central limit theorem. So B is a law of large numbers. C is a central limit theorem. By process of elimination, it should be A, but let's confirm. If I take many different samples and I average them, the mean of my X bar values will be close to mu. The fact that I believe that the average of those will be close to that, that is the unbiasedness, that I expect that my values that I get will be close to the actual true value. Again, three different things. Unbiasedness means I expect my values to be close to mu. The law of large numbers, as the sample size gets large, X bar will get close to mu. And C, if the sample is large enough, X bar will have a distribution that is close to normal. Unbiasedness, law of large numbers, and the central limit theorem. Let's do one where we actually have to do some math. I don't want just these ABCs. I want to do a true, let's do some math problem. So, all right, number 27. The medical college admission test, the MCAT. Almost all medical schools in the United States require students to take the medical college admission test, the MCAT. To estimate the mean score mu of those who took the MCAT on your campus, you will obtain the scores of an SRS of students. Good, it's a simple random sample. Now the scores themselves follow a normal distribution, and from published information you know that the standard deviation is 10.4. Now, suppose that unknown to you, the mean score of those taking the MCAT on your campus is 500. So somehow that's known. So what I have here is I have a normal distribution whose mean is 500 and whose deviation is 10.4. Those are things that I'm given. Now, A, if you choose one student at random, what is the probability that the student score is between 495 and 505? How would I do that? Use any means necessary. How would I get the answer to that question? If you choose one student at random, what is the probability that the student score is between 495 and 505?
Crunch it.
Crunch it. I love it. Let's go to crunch it. Where is crunch it? Here's crunch it. So what am I putting into crunch it? Where do I go on crunch it? Tell me. Walk me through it.
You want to find the probability of the right side of, from the right of 505 and the left of 495. So then you can
wait.
add those.
The right of 505 is between them, isn't it?
No, but like, so you can add those two and then subtract it from 100. So
I see what you're saying. Okay, so tell me what to do.
you put in, let me go back to my notes.
All right. Well, let's go to normal first. Right? We haven't done any of this binomial, the chi-square, the F, the geometric, the Poisson, students T or uniform, but we have done normal. We go to normal. What's my mean?
500.
500. What's my standard deviation?
10.4.
10.4. Do we want less than or greater than? And in either way, less than or greater than what?
$505.
So we want less than 505 or greater than 505?
Less than.
Okay, so let's do less than 505. And we
That's
calculate.
still greater than.
Sorry?
Oh, no, never mind. You're fine.
Okay, so less than 505. So on the graph, 505 is about here. And less than 505, it gave me a 68.466%. Okay, what now? Is that my
No.
answer, or is there more work? Sorry?
We do greater than the, what was it, 495?
Well, if we do greater than 495, that's going to be shading this way, right? From 495 that way, correct?
It'll be less than or equal to 495.
Yeah, we want less than 495. If we do less than 495, then we get 31.534%. So the question is, if I use less than 505 and I get this number, and less than 495 and I get that number, how do I use those two numbers to get what's in between them?
You subtract.
Subtract.
You just subtract them. So 68.466 minus 31.534. I don't know what that is. I'm too tired. 68.466 minus.
It's 36.932.
Okay, so 36.9%, let's say. So the probability of being between 495 and 505 is 36.9%. Definitely know how to do that for the test. Now, part B, you chose to sample 25 students. What's the probability that the mean score is between 495 and 505 now? We're skipping to C. We still want to go from 495 to 505, but now we're not interested in one at a time. Now we're interested in 25 at a time. So how do I calculate that one? Well, the first thing you want to do is you want to ask yourself, is it normal?
No,
Why not?
because it's smaller than 30, so you can't assume that it's normal.
But you're trying to use the central limit theorem, are you not? The central limit theorem says that if the original one is not normal, then the sample is normal if n is large, right? But if the original one is normal, then the sample ones are also normal. Is the original one normal here?
Yes.
Then the sample distributions are normal of any size, which means it is normal. What's the mean of this one going to be?
500.
500. And what is the deviation of this one going to be?
Square root of 25.
So the deviation is 5?
Yes.
You sure?
Wait. No.
2.08. I heard someone say it. 2.08.
Please.
Right? Someone private me and said it's less than 30. It's not normal. But I answered that already. Hopefully you said that before I answered it, because it is normal since the original one is normal. So what we have now is we still have a normal distribution. The only difference is that sigma is a lot lower. Sigma is now 2.08, not 10 point, whatever it started as, 10.4, 10.4. So how do I calculate now the probability that the mean score of my sample is between 495 and 505? What do I do now?
Go to crunch it.
Go to crunch it. What do I change?
The standard deviation.
What should it become? Could I read? Someone asked, can I, wait, before I answered, someone said, can I reiterate why it's normal? Some fancy words there. Can I reiterate why it's normal? It's normal because the original is normal. If the original is normal, then the sampling distributions are always normal, no matter the size. It's only if the original is not normal that we need a large enough sample before it becomes approximately normal. Go back to that applet from last time, and we saw that everything eventually became normal, but normal started as normal and stayed as normal. It was always normal. That's why. Anyways, back to here. What's the deviation?
2.08.
2.08. So if I do the same two calculations, for less than 495, I get 0.008112. And for less than 505, I get 0.9918 9. And I do the same subtraction. I get a much larger 98.4%. Where did the 2.08 come from? I did the original one and I divided by the square root of 25 because my sample size is 25. And the new one is the old one divided by the square root of n. N is 25. So take 10.4 divided by the square root of 25. We are now dealing with an n of 500, 2.08. First one is 0.3688. I got 36.9%. And the last one was 98.4%. So my rounding was a little different because I wasn't taking the time to be 100% accurate, but it's still fairly close. Are there any questions? Oh, where did that come from? Are there any questions on that? You know, let's take a look at my Zoom. Did it work? Oh, it's still going. Almost done, so close. So what are the odds on whether or not it's going to say error or it's going to go through? Are we taking bets?
Let's use crunch it.
I'm not sure how to put in the data, but we'll come back in an hour. We'll see if it's done yet. All right, let's see. Let's see if I get another question. I mean, they're all pretty much the same. So let's do 37. I'm betting 400 extra credit points. Wait, so what's your bet? Are you saying that it's going to do it and give me an over under that it won't load, that it'll say error? Well, okay. Well, what do you get if it does not? What do I get from you if it does not say error? If it actually goes through? Pride? I think I give a shit about that. All right, so. Yeah, take points off the exam. Now we're talking. I actually used to have a rule. Because I used to play chess competitively before I stopped. And I used to have a rule that if any of my students can beat me in a game of chess, they get an automatic A. But if they lose, they get an automatic F. So I only had one student take me up on the offer. In all my years of teaching. I can do 2 out of 3. I mean, after you lose the first one badly, you're not going to want to play again, but whatever. I'm not saying people aren't there that can beat me, of course. I mean, plenty of people can beat me. It's just people who don't play competitively are not gonna beat me. No, he didn't win. But before he actually played, it was blitz. Yeah, 2 minutes. I have a chess clock. But before he actually played, he said, I can't really do it for an A or an F, but how about the winner gets a steak dinner from the loser? I said, okay. That was a good steak. That's all I can tell you. That's all I can tell you. That was a good steak. And, ooh. No, no, that wasn't it. Is it going? Is it going? Come on, man. It's green. Green is good. Green is good. Come on. Just show me you got it. It usually appears down here at the bottom. I'm feeling this. He's going to owe me a steak. Anyways, okay, let's go back to the question. Then we'll come back and look at it. So it says green is not good all the time. What do you mean green isn't good all the time? You're saying that can be green and still be bad? I take my steak green. Come on, man. I'm feeling this one. I'm feeling certain situations green is bad. I guess, like celery is bad and parsley is bad. And spinach is good. We all like spinach, but come on, show up. All right. Anyways, let's get back to work. So to estimate the mean square mu of the Veggies are good, gross. To estimate the mean score mu of those who took the medical college admission test in your campus, you will obtain the scores of an SRS of students. From the published information, you know that the scores are approximately normal with a standard deviation of about 10.4. So right now, this is what we have. We have normal of blank 10.4. They didn't give us the mean yet. Maybe they will as we read further, I don't know, but they don't give it to us yet. You want the sample mean X bar to estimate mu with an error of no more than 1 point in either direction. What standard deviation must X bar have so that 99.7% of all samples give an X bar within 1 point of mu? So, who here has a thought as to this one?
Based off of what we know from the rule given, we would need two sigmas worth of deviation from the mean.
Well, hold on there, buddy. Can you read me what's in parentheses over there?
Use the 98, 95, 99.7 rule.
Well, it's 68, first of all, not 98. Okay,
68.
But second of all, what do those three numbers tell you about how many deviations?
One deviation away from the mean is 68% of the data.
Yeah, and 2 deviations?
Is 95% of the data. Oh, three.
Yeah.
I need my coffee.
So 3, right?
Yeah.
Okay, Ryan, you know how I like my steaks. But there we are. It went through. Crazy talk. Okay. So I want 3 deviations to be within 1. I want 3 deviations to be within 1 point of the mean. And the question is, what must my sample size be? How do I get, remember, as your sample size gets bigger, the deviation gets smaller, right? So someone tell me, what is a good formula for this problem? I've already done it here. So my answer, let's see if it's right. My answer is 974. Boom, 974, I love it. Okay, so someone tell me how I got that. 974 was my answer. How did I get 974? Where did that come from? So, what is the standard deviation again for the sample distribution?
10.4.
That's for the original distribution. For the sample distribution, what's the standard deviation? What is the standard deviation for the sample distribution? It is 10.4 divided by what?
Divided by the sample number. And then did you solve for
Wait. It's not divided by the sample number.
It's square root of the sample number.
Okay, 10.4. So Jaden, it's not 1.04 because I don't know what n is yet. It's 10.4 divided by the square root of n. Currently, n is unknown. That's what I'm solving for.
Yeah.
But it's 10.4 divided by the square root of n, correct? And I want that to be so small that 3 of those give me what?
99.7%.
No. 3 deviations will always give me 99.7%. That's a percentage, but I want 3 deviations to equal what?
Oh.
I want 3 deviations to equal 1, the number 1. It says you want to estimate it with an error of no more than 1. I want 99.7% of my data to be no more than 1 unit away from the mean. So whatever the mean is, I want the distance between the mean and 3 deviations out to be a distance of 1. And what is that formula? 3 times 10.4 over the square root of n is equal to 1. And then just solve for n.
So 10.4 squared.
3 times, no, the square root of n equals 31.2. Right? If you do the math, you get the square root of n equals 31.2. And then if you square both sides, you get n equals 973.44. And we always go up when it comes to numbers, so n to 974. Let's look at their work. It'll be exactly the same as mine. We need to choose n so that 10.4 over the square root of n is 1/3. I did 3 times that is equal to 1. Same thing. The square root of n equals 31.2. So n equals 973.44 because n must be a whole number. Take n equal to 974. What a lovely question based upon what we've been doing. Are there questions on that?
Can you say we round up because what?
Well, the reason why you round up is because exactly 973.44 students or people will be the exact amount necessary so that my error is not too big. But I can't have 973.44 students. That makes no sense. If I have fewer students, my error is going to be larger. So if I go to 973, my error is too big. But if I have more students, my error will be even smaller. And I'm okay with an even smaller error. I just don't want a bigger error. So you always go up when it comes to people because sample sizes that are larger never hurt. Sample sizes that are smaller, on the other hand, can. Does that make sense?
Yes.
All right. And all other questions here are going to be variations on a theme. So let's go ahead now and start with confidence intervals, the basics. The beautiful thing about confidence intervals is that confidence intervals are very formulaic. Once you have the formulas down for confidence intervals, it's lots and lots of plug and chug. And in fact, I'm sure Crunch It will have confidence intervals. Maybe. Anyone ever see any confidence intervals on Crunch It? No. Come on, Crunch It. You're better than this. Where are your confidence intervals? Hold on, it's got to be here somewhere. We'll have to find it eventually anyways, so you might as well.
I think it's under proportion sample 2.
For proportion?
Yeah.
Well,
And then 2 sample.
oh, here we go. Yeah, confidence intervals. Okay, no, so it was there. I just missed it. It would be there for Z as well. Right here, confidence intervals. Okay, good. So yeah, they definitely do it. Can you chop the person to point? Okay, so confidence intervals, the basics. So here's the idea. Suppose you want, I keep using this example because it's just such an easy example to use. But suppose you want to calculate the average height of every American. So what do? You take a sample. Now, when you take your sample can have any value. let's say it has 5.8. So, and suppose you have a large sample, so you're pretty confident that it's close to the true value. Okay, but how confident are you? Are you saying, well, I'm pretty confident it's between 5.7 and 5.9, between 5.6 and 5.10, between 5.5 and 5.11? We want to create these intervals of confidence. I'm 95% confident it's in here. I'm 99% confident it's in here. I'm 20% confident it's in here. Of course, why would you ever want to be 20% confident? We usually pick higher levels of confidence. But in general, every confidence interval will be based upon how confident you want to be. This is all under statistical inference. Statistical inference is when you take your samples and you get your data and you infer things about the population from your data. My data gave me that, therefore I can conclude the population will have some property, okay, that the true value is around here, or this, or that, or something. Statistical inference is what statistics is all about. We're going to start with making confidence intervals for a mean, okay, and we need 3 basic conditions to do this. 1, it's got to be an SRS. Okay, most of the formulas that we come up with in this book are going to assume a simple random sample. Most of the questions that you get are going to be assume that you have a simple random sample, because if you don't have that, you really can't do anything. We're not going to have any non-response or practical difficulties. We're just going to ignore that. Okay, you're not going to have any questions like that. You might have a conceptual question like, you know, hey, when is this a problem? You should know when it's a problem. But none of the mathematical questions that you're going to have to deal with are going to have any problems. And you want the population to be large compared to the size of the sample. Okay, if the population and the sample size are similar, there are problems with the math that we're not going to go into. So just you want a large population relative to the sample. Again, when it comes to the math, you're never going to have to worry about that. 2, at this point, we are assuming that whatever you're trying to measure is normal. Okay? We will talk about what happens when it's not, and we will develop other situations or other things to do in that situation. But for now, we are assuming that you're dealing with a normal population where you do not know the mean, but you do know the standard deviation. We're going to have, I think, 8 or 9 different formulas for all these different cases. This is case 1. It's normal. We don't know the mean, but we do know sigma. And some ancillary conditions like it has to be an SRS, and the population is large compared to the sample, and there's no undercoverage or non-response situation. Okay? The general rule is the population is large relative to the size of the sample will be satisfied if the population is 20 times as large. That's going to be our condition in the book. The population is 20 times the size of the sample, then you're good to go with this technique. Okay? Now, how realistic are these assumptions? Not always, but as we move on in the book, we'll start worrying about the situations where they're not. For now, we'll keep it very straightforward. Okay? So the question is, what do we do in that situation? How do I go next page here? Okay, so this is not, oh, there's questions for each section. That's why. Okay. So this one I saw already. It's not important. Okay. So 16.2. This is the general look of every confidence interval that we are going to be dealing with. They will always be your estimate plus or minus your margin of error. Every confidence interval that we develop, and we will have 8 or 9 of them, every confidence interval will have the shape estimate plus or minus the margin of error. In my height example, the estimate was 5.8. plus or minus 1 inch, plus or minus 2 inches, plus or minus 3 inches, whatever my plus or minus was, that's the margin of error. That's how willing you are to be a little bit off. The margin of error. The estimate, that's just going to be your sample mean. When you take your sample and you get 5'8", 26 pounds, 27 years, whatever it is that you're measuring, your sample mean is your estimate. And their example, where they had a 95% confidence interval for the mean BMI of young women, their sample mean was 26.8. So, and their uncertainty, their margin of error was 0.6. Nothing to do with degrees of freedom, nothing to do with that at all. We will be doing with degrees of freedom later, but this is not that at all, okay? So you have your estimate, that's your guess, your best guess, and then your margin of error. Now, the best guess, your estimate, that's just the values that come from your sample. That's got nothing to do with the confidence or anything. That's just, this is the average of my values. But the margin of error depends upon how confident you want to be. So let's imagine conceptually what's going on here. You want to know the average BMI of young women in America, like they do here. Now, the average BMI is somewhere on the number line, right? It's somewhere between negative infinity and infinity. Of course, you can't have a negative BMI, so it's really 0 to infinity. I don't know what a physical lowest possible value is or a physical highest possible value is, but for the sake of argument, let's just say it can be anything on the number line. Those are the possibilities. You want to, excuse me, you want to do a study, excuse me, you want to do a study that determines the average BMI. So you do your study and you get 26.8. Now, can you conclude with certainty that if your study gives 26.8, that the actual value, the true value, is 26.8? Your sample is 100 people, you got 26.8. Is that the true value for every young woman in America?
No.
Probably not. Unless you got very lucky and just coincidentally happened to get the right answer, chances are not. So what we do is we say, okay, I know it's not exactly 26.8, but I'm going to create an interval around it. And I want to be fairly certain it's in there. I can be 90% confident I caught it, or 95% confident I caught it, 99% confident I caught it. First question. As you increase the confidence, will the interval get wider or will the interval get skinnier? Remember, the confidence is how confident are that you caught it, that it's actually in there. Sorry. As you increase the confidence, will the interval get wider or will the interval get smaller? What do you think?
It should be smaller, right? Because if you're more confident about it, then that means...
Well, let's think about it. If I give you an interval this size, how certain are you that the true value is going to be in that interval? But if I give you an interval this size, are you more or less confident that you caught it? Yes, exactly. Yeah. And someone else above that, Bernadette, both of you. The more confident you are that you caught it, the wider that it has to be. Think about it. If you want to be 100% confident that you caught it, just take it infinitely wide. There's no question you had it. Right? The more confident you are in catching it, the wider the interval is going to be. The less confident you are, the smaller it's going to be. Right? So if it's extremely small, I'm not confident that I caught it. Well, if you're not confident that you caught it, what are you going to do with that? So we're looking for like a balance. We want high confidence, but we don't want the interval to be too large. So we got to figure out how to do this. Now, if you take a larger and larger sample, how confident are you that you're going to catch it? If the sample size gets larger, do you think the confidence interval gets smaller or the confidence interval gets larger? Excellent. Smaller, right. The bigger the sample size, the smaller the interval, because you don't need a larger interval to make up for the confidence. The larger sample size is giving you that confidence. So if I want to make my sample size small, my confidence interval smaller, just take a larger sample size. Okay, we don't want to lower our confidence because we want to be confident that we caught it. We really don't want to change the confidence. But if you want to be more confident that you caught it, just make the bigger sample size. That will make a smaller interval. Okay, so let's do an example. Let's do an example for the next section where we actually calculate a confidence interval. Okay, so I don't want to use these formulas. I mean, I do, but I want to first give an example so we can see it on Crunch It. So how do I find one? Okay, we might have to do it like this. Okay, so let's ignore this for now. We'll get to that later. Let's look at example 16.3. It says good weather, good tips. Does the expectation of good weather lead to more generous behavior? Psychologists studied the size of the tip in a restaurant when a message indicating that the next day's weather would be good was written on the bill. Here are tips from 10 patrons, or patrons sounds good. 10 patrons measured in percent of the total bill. Okay? This is one of 3 sets of measurements made, the other being tips received when the message in the bill said the next day's weather would be bad, would not be good, or there was no message at all. But we're ignoring those for now. We're not going to compare them. That'll come later. We're just looking at this one set. We want to estimate the mean tip for comparison with tips under the other conditions. But for now, we're just going to do this one. So I'm going to load up Crunch It in a new window so I can see both at the same time. And I'm going to put these values in. So 20.8, 18.7, 19.9, 20.6, 21.9, 23.4, 22.8. I'm not going to say them. Just tell me if I screwed up.
If you tap the Crunch It sign, it'll load it on its own.
What Crunch It sign? Crunch It. Crazy. Was there the whole time? Awesome. I love you. You're the best. Whoever you were. Okay, so we have the data here. So we're going to go now to statistics, and we're going to go to Z, and we're going to go to one sample, a confidence interval, and let's see, the book wants a 95% confidence interval. So we're going to use a 95% confidence interval, and we're just going to calculate. Oh, it wants a sample. Where was sample? The sample is here, right here in the 16.3. And then I hit Crunch It, and it just went right there. That was amazing. How did I get where? I'm not sure what your question is. From Crunch It. Oh, what did I do on Crunch It? So again, I went to statistics. I went to Z because it's normal. We were told it's normal. Remember, that was one of the 3 conditions. It has to be normal. That's Z. And it's one sample. It's not 2 samples. It's just one sample. So then I went to confidence interval, put in 95%. Remember the rules, we have to know the standard deviation. So here, it says right here, we know from past experience that sigma is 2. So they know it. I didn't know it, but they know it. And I'm going to use my sample labeled as percent. So I'm going to use my percent. But you know what? I just realized that this, yeah, okay. And then I'm going to hit calculate. So this is a few pieces of information here. One, it tells me how many data points I have, 20. I have 20 data points. The sample mean was 22.21, which the book agrees with, right? X bar is 22.21 right here. And then it gave me the 95% confidence interval to be 21.33 to 23.09, 21.33 to 23.09. So there it is. So the question is, how do we interpret this confidence interval? What does this mean? Well, on its surface, it means the following. We are 95% confident that the true value is between 21.33 and 23.09. Are we any more confident that it's in the center of that interval than the left edge or the right edge? No. We have no preference for any one point in that interval over any other point in that interval. All we know is that we are 95% confident that the true value is between 21.33 and 23.09. So if someone came along and said, I'm pretty sure the true value is 20%, you would say, well, not according to my data, because according to my data, the true value is between 21.33% and 23.09%, and 20% is not in there. If someone said, I believe the true value is 23%, what would you tell them? If they said, I believe the true value is 23%, you would say, well, my data does what?
Supports that?
Yeah, it supports it, exactly. Right? The fact that it's on the very edge, I can't say one thing about one point in that interval more than another. 23% is in that interval. My data supports that it might be 23%. I can't conclude it's 23%, but it supports that it's 23%. Now, that's the common understanding of what a confidence interval is. But in reality, it means this. If you take lots and lots and lots and lots and lots of confidence intervals of size 20, 95% of them are going to contain the true value. Not every confidence interval is going to catch it. Remember, we're not 100% confident. We're only 95% confident. 95% of your confidence intervals of size 20 are going to catch the true value. But the easiest way to interpret it is that we are 95% confident that the true value is between 21.33 and 23.09. Okay, but if you make, in fact, there was a good picture in the book before that I kind of skimmed. Let's go back to it. It might have been the previous section. If you create a bunch of confidence intervals, you see that most of them catch the true value, but some of them won't. All right, 25 samples gave these 95% confidence intervals. In the long run, 95% of all samples give an interval that contains the true value. So my 95% confidence interval is just an interval. If you make lots and lots of them, 95% of them are going to catch it. But the easiest way to interpret my specific interval is that I am 95% confident that it's in there. So if my value is not in there, if someone said, I think it's 20%, you say, my data at 95% does not support that. Would my data support it for 99%? Well, let's go to confidence. Let's go back to crunch it. And let's check the same data Only difference is we'll make it 99%. What happened to my confidence interval when I upped my confidence from 95% to 99%? Notice
Wider.
it got wider, right? If we look at our values, before they were, where do they go? Before they were 21.33 to 23.09. And now this one dropped, this one got bigger. So greater confidence, and it gets wider. So what is the formula for the confidence interval, for this basic confidence interval? It's right here. It is X bar, that's my estimate, X bar, plus or minus the margin of error. What's the margin of error? Z star sigma over the square root of n. What I want to do in our example is show you how by hand they got these values. Okay? And that'll be the last thing we do today. And we'll start again here next time is a test, of course, but the time after that we will recap this a little bit. So where did X bar come from? Well, if you look at Crunch It, that was your sample mean. That is your best estimate. It's just the average of all of them. So 22.21. What was sigma? They told me sigma was 2. What was n? My sample size. My sample size was 20. The question is, how do they know that Z star is 1.960? So that's the part that I want to show you. So make a number line. No, sorry, not make a number line. Make a normal curve. Make a normal curve. And this is the standard normal. So what is the mean of a standard normal distribution?
Zero.
0. So the center is 0. And we want a 95% confidence interval, correct? So I want you to go out in both directions until you've obtained 95% of your data. I want you to go out in both directions until you've obtained 95% of your data. How many deviations is that, 95%?
2.
That's 2 deviations, right? That's a 68, 95, 99.7 rule, right? Well, it's not exactly 2. It's exactly, or it's closer to 1.960. So let's see how I can get that exact or close to exact value, 1.960. Let's go to Crunch It. And let's do a normal. And this time it's quantiles. And we're using 0, 1. But what number are we going to put in here? That's the question. So remember what quantiles is. It's how much is to the left of that value. We're looking for this number right here. How far we got to go until we've obtained 95%? What's to the left of this value right here? What percentage?
2.5.
Well, no, that's to the right. How much is to the left? Right? Is this your left or your right? What do you guys see when you see this?
That's my left. Is it 97.5?
97.5%, right? To the left of that is the 95 that's in the middle, plus half of the 5% that's on the wings. 2.5 on this side, 2.5 on this side. So to the left of this point is 97.5%. So if I go and I put in 0.975 on Crunch It and I tell it to calculate, what number does it give me?
Here's Z.
Sorry?
1.96 if you round.
Yeah, exactly. 1.959963984500536. If I really wanted that many decimal places. But they rounded to 2 decimals, and that's where they got 1.96 from. So if you want to do it by hand, that's how you do it by hand, right? If the confidence is 95%, that means you have 2.5% in each wing, and all we're going to do is calculate what that number is that has 97.5% to the left. If it was a 90% confidence interval, so there's 90% on the inside, how much would be to the left at that point?
95.
95%. They claim that 95% gives me 1.645. Let's put in 95%, and they give me about 1.645. So that's where these numbers come from. Okay, you can memorize them. You can write them down. They're used so often, 1.645, 1.960, 2.576, because these are the basic confidence levels. Most of your homework questions will use 90%, 95%, or 99%. 95% interval, 90% interval, even on Crunch It. When you go to Crunch It and you just do a generic confidence interval, so you just clear everything and you say, let's do a confidence interval. Well, before it was 95%. I think it changed because I made it 99%, but it just assumes 95%. Those are just the standard numbers. So you can either memorize these, write them down, know how to calculate them, or just use Crunch It. But the general formula for the standard basic confidence interval, assuming it's an SRS of size n from a normal population, where you do not know the mean, but you do know sigma, a level C confidence interval, 95% or whatever confidence interval from you is the estimate plus or minus your Z star value. That's either 1.645 or 1.96, whatever the case may be, sigma over the square root of n. And all you do is you go to Crunch It and you have it do it for you. And that gives you your confidence interval. We will, again, continue this next week, Thursday. I'm going to stop recording for now.